Okay, we start from where we ended last time, that is we discussed conditional density, conditional probability density. We consider two random variables x, y. Now, I just generalize it to three random variables, and then I mean you can yourself think of any number of random variables, jointly random variables. So, suppose we have got now three, various cases will emerge. Suppose x, y, z, three jointly random variables. So, there will be one axis for x, another for y, another for z. Suppose I consider a point, this is x, and then this width is dx. So, x plus dx. Similarly, I consider up to this and then this much is dy. Okay. So, this is that box. We are familiar with this because we considered two random variable case last time, but now z also we take up to some value small z and then dz. So, we go up here okay. So, this much is dx, this much is dy, this much is dz. So, we know probability of this pair x, y, z falling within this cube will be proportional to the volume of this, if of course, and if the widths dx, dy, dz are very small, then that proportionality can be taken to be linear. That means, we can, I am just generalizing, same logic. So, probability of what? Capital X lying between x plus dx to x simultaneously with capital Y lying between y plus dy proportional, and then to y, and capital Z lying with between small z plus dz to small z. This will be proportional to the volume. Larger the volume, higher will be the chances. Smaller the volume, less will be the chances. And if the width dx, dy, dz each is very small, infinitely small, proportionality can be taken to be linear. So, it will be a proportionality constant p times dx, dy, dz. P will, and I write here x, y, z to indicate the random variables involved, and this will depend on the location in which the box is located, that is this point. Okay. This point gives the full idea about the entire all the other vertices. If I move the box to some other place in this three dimensional space, dx remains same, dy may remain same, dz may remain same, the probability will change. Obviously, there is no guarantee that you will have the same probability of this x, y, z triplet occurring in the box if it is here and also if it is there, they will be different. So, it depends on the location of the box. That is why it will be a function of this location which we take to be x, y, z. because once x, y, z is known, other points are known. This is called again joint probability density. As before, if we integrate it from minus infinity to infinity, and there will be triple integral, that is certainty, because the pair will always lie within this 3-dimensional space, where capital S goes from minus infinity to infinity, capital U goes from minus infinity to infinity, capital Z goes from minus infinity to infinity. So, that will be again 1, and all other things follow, fine. So, this is the thing, but now I can bring in the concept of conditional probability density in various ways here. Okay. One way, assume capital X is restricted to x to x plus dx. That is, we are considering only those cases where capital X is occurring from here to here. Other cases we are not considering. Other cases occur, we are only considering this. So, this is kind of fixed. Within those cases, what are the chances of capital Y falling from small y to y plus dy simultaneously with capital Z falling from small z to z plus dz? All right. That is y in this much and dz in this much, dy dz. So, what is the probability that capital Y and capital Z lies in this plane, this side, which could be anywhere here, depending on the particular value capital X takes, whether here, here, the probability of the side, this side, this is dy, this is dz. So, it will be proportional to the area of this, right. So, subject to this, subject to the above probability capital Y lying between small y plus dy, capital Z lying between small z plus dz, subject to this way we write, subject to the condition that capital X lies between small x plus dx and x. So, that will be linearly proportional to the area of this, and so it will be a proportionality constant, which is p times dx dy dz, and this p again will depend on the location, because the entire thing will change if I move the box elsewhere, even if the size of the box remains same. So, this p will be a function of x, y, z, but that I write in this manner. We follow a convention. First, we write those variables y, z, which are free, this by the constraint. Capital X is constraint, and then y and z are taking various values. So, free variables by the constant variable. This is the notation, but actually it is a function of these three, and that corresponding values are y, j small z by small x. All right, capital X is small x, capital Y takes small y, capital Z takes small z. So, this is a conditional probability. What kind of condition? That capital X is subjected to remain between x to x plus dx. Subject to that, probability of capital Y falling between y to y plus dy and z from j small z to z plus dz is this times dy dz. So, this is one conditional probability density. Okay. So, then overall chance of capital X, Y, Z lying within the box will be how much? First, we subject capital X to lie here and then find the probability of Y, Z lying within this box, any box. That times, now I have to multiply that by the chance of capital X lying here, lying from here to here. So, the entire box will be covered. First, I fix it here, capital X I fix within this. Subject to that, I find the probability of capital Y and Z lying in any of these planes, any of these square planes, that will be proportional to this. Now, the chances of capital X really occurring from here to here, I have to take that, multiply that probability with this, then that will be the overall chance of capital X, Y, Z lying within the box. Therefore, this thing, same probability of the same thing I am writing. Instead of writing there, I can as well erase this, no need to rewrite the same sentence. And this is equal to then this probability or this quantity. This is equal to this in one way, and the same thing will be, I have to multiply this by into the chance of capital X lying from here to here, which is, we have seen this. So, if I now equate the two, we get this relation joint density because dx, dy, dz common on both sides and they are positive. So, you can take them common. So, that is a product of either here these are the two free variables, then constraint x. So, value of capital Y is small y, value of capital Z is small z by value of capital X. These times, so if it is a constraint variable, so now there will be another probability density of this, which is constraint variable. So, probability density of that alone will be here. All right. But I can view this in another way. Okay, I can for that matter think that suppose we are constraining not only capital X, we are constraining capital X and capital Y both. Capital X will lie from here to here, capital Y lie from here to here. So, this is the zone in which capital X, capital Y will figure, but capital Z can vary. Okay, capital Z can vary from here to here anywhere. Like capital Z could be like this. From small z to z plus dz. So, this is a line. So, that chance will be that is subject to capital X lying here and capital Y lying here. There is that capital X comma Y pair lying on this square, capital Z lying from here to here. So, could be here to here, could be from here to here, could be from here to here, could be from here to here anywhere, but that will be but on this. So, that will be proportional to the height of this, okay, by the same argument. So, you can also work like this. Then we go to the next page. So, with reference to that, probability of just capital Z is the free parameter now. Subject to capital X lying from simultaneously that will be proportional to just dz, and I take it to be linearly proportional because dz is so small. So, probably this constant proportionality constant will be p, and it will be again the 3 random variables are x, y, z, but now I write again in that form. First the free variable or variables, here only one is a free variable. So, z by the 2 constraining variables now, which are constrained to remain here and here. So, they come next. So, their values also capital Z is small z divided by small x small y times dz. So, then probability of x lying between small x to x plus dx, capital Y from small y to y plus dy, and capital Z from small z to z plus dz, which we already have seen in terms of joint density. This again we can view this probability multiplied by the chance of this happening. First I am assuming this is fixed, this has already happened, and then what is the probability of this? This is this much. But what is the probability of this event happening? That times this. So, that will take care of the overall thing, that is capital X lying here, capital A lying here, capital Z lying here simultaneously. Okay. So, that will be this probability, this chance factor then this happening together means joint density, x lying here, y lying here. So, if you get the two and forget about dx, dy, dz, they are common. See, now you can write p x y z as p z by x y small z previously you have seen that time only x was constrained. So, it was y z, does not matter y z or z y, I am just writing y z by x, and then this is. So, you see out of all the variables you can put some to be free, like y z were free subject to the constraint. So, this was constraint. So, put like p probability of y z condition to capital X. So, y taking value small y, z taking value small z, this capital Z and capital X taking value small x, times the probability density of the variable or variables which are constraint. Here I had y z free and x constant. So, it was multiplied by probability density of x only, there is only variable under constraint. Here I took x y together under constraint, subject to that capital Z was free to take values. So, z by x y, then it is x y. If it is y z by x, then it is x. Similarly, if it is x z by y, then it is y. If I could have had x z by y, then it would have been y, capital Y. Accordingly, small x, small z by y and y, small y. All right. So, you can take these variables, take some of them to be free by some of them others which are constrained. So, that is a conditional probability that is subject to these constraint variables taking certain ranges, what is the probability of the other variables falling within certain other ranges. That times now we have to take the probability density of this constraint variables, joint probability density of the constraint variables. Okay, this is a general result. Now, certain things follow from here. Suppose we are given a function f of x. Okay, it has only one variable, but I want to find out E x y of f of x. In general, any function whether x or y of f, if I am taking E x y, it is nothing but take the double integral of the function small x within integration, because it is a integration variable. Capital X was the general notation of the variable, random variable, but small x is the actual integration variable, the value on the axis, x axis at a point. So, this is to multiply it by the joint density, because expected value with respect to two variables, even if inside, right, this function is such that it depends only on capital X, does not matter. What is the average value with respect to capital X y? So, I have to multiply it by the joint density as before. Then what I see, this is f x. So, I will now use this relation. I will take multiply by a conditional density. I will take y, whatever is not figuring here, that to be free variable, by whatever is figuring here, that to be the constraint variable. So, p y by x, small y by x, and if that be, then I have to multiply it by p capital X small x, y by x and x, y by x, that is first x is capital X is constraint, then probability density, conditional density, and then this is multiplied by the probability density itself of capital X only. Okay, I will take it this way, because you will see what happens after this if I choose this way. F x p x x, it is a function of x, it is a function of x. Okay. So, but they do not have any y. So, I take them out in the outer integral. Inner integral is with respect to y. Now, what is the meaning of this integral? I know what is the meaning of this. Meaning of this product is, if capital X is constrained within the zone small x to x plus dx, that is fixed, not changing, then what is the probability of capital Y lying between small y to y plus dy? So, that is proportional to dy. And this integral gives thus the same probability, but from minus infinity to infinity. That is, I mean this is capital X y, this much is small x, this is dx, this is y, and this much is dy. So, probability of this pair, I mean subject to capital X lying between here to here, probability of capital Y falling from here to here is proportional to dy, and this much was the proportionality constant. So, this much is the probability. And if I integrate from minus infinity to infinity means subject to this constraint, what is the probability? Subject to this constraint, what is the probability, net total probability of capital Y lying on this line from minus infinity to infinity? Again, that is certainty, because even if capital X we are constraining here and then observing capital Y will always occur from minus infinity to infinity. It cannot have any other value. So, probability of capital Y taking a value from minus infinity to infinity, even with this constraint, that is 1, because that is certainty. Even under capital X lying from only here to here, it does not matter. Chances of capital Y occurring from minus infinity to infinity under that condition, even that is 1, because that is certainty. Even if capital X is kept, chosen to be from here to here only, capital Y will always occur from minus infinity to infinity. It cannot occur it cannot take any other value. So, total probability of that which is given by this inner integral, this is 1. So, this is equal to 1, and therefore, I am left with only this much, and this is nothing but original function multiplied by its probability density, the original function of random variable x multiplied by its probability density and integral from minus infinity to infinity. So, that is the expected value if you go back to the definition of the same function with respect to f x with respect to x. So, if there is no argument, I mean if in the argument of the function, if one random variable is not figuring and we are still taking E x y, then you can jolly well drop y and write like this, just y is gone here. It is like taking the expectation of f capital X with respect to capital X alone. Okay. Alternatively, another example, suppose you got 3 random variables x, y, z, and there is one function still, suppose x, y. So, this is again triple integral now. Function as it is you put, but with small x, small y, and then the joint density. Here, these are the free random variables x, these are the these are figuring within the function capital X which takes a value small x here, capital Y which takes a value small y. So, x, y they figure here. So, as I told you, our policy will be to set z to be free and capital X, y to be the constraints. So, this I will write as P capital Z free, sorry, P capital Z by x y, they are capital X y, they are under constraint, they will take values from certain range, subject to that probability density of capital Z, there is a probability of capital Z lying between small z to z plus dz. There is this conditional probability. So, capital Z takes value small z by into this we have derived earlier. Now, the probability density of these two constraint variables, joint variables. What happens then? This integral I can write as outer integrals f x y and this p with respect to dx dy, because they do not depend on z, and the inner integral with respect to z, that is small z dz. Again this is equal to 1, because you are constraining capital X and y to fall within certain area. Under that, probability of capital Z occurring from small z to dz was this much. And now, the integral is under the same constraint, probability of capital Z lying from minus infinity to infinity. That will always happen, capital X and Y may be constant, but even under that capital Z will always occur between minus infinity to infinity. That is certain to happen. So, this is certainty, its probability is 1. And if that be, I am left with this much only, which is a function multiplied by the function of two random variables multiplied by the joint density of those two random variables and integral, which is nothing but just E x y z gun. This again shows, even if we have a series of random variables here, but the function contains only few of them, and then you are taking its expected value with respect to all, then you can drop those random variables which do not figure here, like z was not figuring here, and you see z has gone. So, you can drop them. So, I stop here now, and in the next class we begin from here. Thank you very much.